Hey guys, welcome back. So we're taking a look at 7.5, the double angle identities. So over here, again, we're looking at sine, cosine, tangents. These are double angles. So you actually notice that these are based on the sum identities, where instead of having A and B, they're the same thing, theta and theta, and it creates these equations. Now, because cosine 2 theta's main equation is cosine squared minus sine squared, both of which are based on the Pythagorean identities relating cosine squared and sine squared, there's two other possibilities you could work with. So depending upon the problem, what's given to us, we're either going to use the 2 cosine squared minus 1 or the 1 minus 2 sine squared. Very rarely would we want to use cosine squared minus sine squared. That's more if something kind of shows up more with like a trig proof, recognizing that means cosine 2 theta than anything else really. So let's explore. So here we've got sine 2 theta. We're given sine single theta is 4/5. And we're told theta is between 90 and 180, which means we are operating in quadrant 2. So for this problem right here, because sine 2 theta is equal to 2 sine theta cosine theta, we need to find cosine theta to fill into the formula. Well, so this is very similar to what we did in 7.1 with our fundamental identities. Given one trig function, find another. So if we're given sine, how do we find cosine? Well, cosine squared equals 1 minus sine squared. So we'd have 1 minus 16/25. The 1 is really a 25 over 25, which gives us 9/25 for cosine squared. Square rooting gives us 3/5. Now, whether that's a positive or negative 3/5 depends on the quadrant location. Quadrant 2 cosine is negative, so we have a negative 3/5 there. So for our sine 2 theta, we're then doing 2 times 4/5 times a negative 3/5, and we get sine 2 theta to be, because 2 is really like 2 over 1, a negative 24 over 25. You'll notice that sine single theta is 4/5, but sine 2 theta is negative 24/25. Because while yes, theta is in quadrant 2, 2 theta would really be from 180 to 360, which is the combination of quadrant 3 and quadrant 4, both of which sine is negative, so it kind of makes sense it's negative. However, that's not going to always necessarily be the case that the answer is always negative or always positive in both of the two quadrants. So it really just kind of depends on the scenario, what's going to happen there. But do recognize that you could have a situation where it's positive in one, negative in the other. So you really don't want to trust the quadrant location of 2 theta. You want to trust the calculation of the single thetas and then how it kind of works out for that problem. Okay, so next up is cosine 2 theta. Here we're given tangent is a negative root 14 over 6. And theta is in between 630 and 720. So we're going to have to subtract 360 first off. Figure out where the heck we actually are operating, because that's beyond our unit circle. And that's equivalent to being in between 270 and 360. So we are operating in quadrant 4 for single theta. Important behind our calculations. So for cosine 2 theta, we're either going to use 2 cosine squared minus 1 or 1 minus 2 sine squared. Because typically, in order to use the other one, cosine squared minus sine squared, we need to know them both. And for the most part, if I know cosine, I can get sine, or if I have sine, I can get cosine. But why then? Because we only need one of them in the other formulas. Now, tangent can give us secant using the Pythagorean identity, and then secant is reciprocal to cosine. So we're going to go that way to get our cosine value. So secant squared is 1 plus our tangent squared, negative root 14 over 6 squared. So we get 1 plus a 14 over 36, which reduces down to 7 over 18. So my 1 is really 18 over 18. That gives us a 25 over 18 for secant squared. Square rooting that gives us secant to be 5 over root 18, which is 3 root 2. I'm not going to worry about rationalizing it because cosine, you just flip that right there. And now there's no need to worry about rationalizing. Cosine is 3 root 2 over 5. Also, even if we wanted to, because we're going to have to square the expression, squaring is going to get rid of the radical anyway, so it'd be kind of a waste to try and rationalize only to square it all away. So cosine 2 theta, not cosine squared, cosine 2 theta is going to use cosine squared. It's going to be our 2 cosine squared, so 2 times 3 root 2 over 5 squared minus 1. Reversing the squaring process, from the square rooting, so we know that this is actually going to come back out to being the 18 over 25. The 1 really then will be 25 over 25. Multiplying by 2 gets us to 36 over 25, which then gets us 11 over 25 for cosine 2 theta. And again, it's a positive value as it's been worked out, and that's perfectly fine. We don't need to worry about where the double angle quadrant is actually located because it's going to be in 2 quadrants. Odds are one of those 2 quadrants will be negative, the other one will be positive, so not really helpful. We trust the calculation. We trust the process. All right, so that's the general idea for the cosine 2 theta. Use what's given to you to figure out either sine or cosine. Substitute into your formula. As for tangent 2 theta, again, quadrant information kind of important. Let's subtract 2 pi here. Figure out where we're operating in. Pi to 3 pi over 2, so we're operating in quadrant 3. So tangent single theta will be negative, positive, but tangent 2 theta could be, positive or negative based on the calculation as it works out. If I have sine, so we want to be able to get to tangents, so let's see. The quickest way probably is to take sine and get cosine. Cosine squared is 1 minus sine squared. So the 1/4 squared is a 1/16, so my 1 is really 16 over 16. So cosine squared is 15 over 16, square rooting that. Cosine is a root 15 over 4. It'll be a negative, though, because we're in quadrant 3. So then tangent, single theta, is sine divided by cosine. If we're dividing by a fraction, we're multiplying by its reciprocal. So the negatives and 4s would both cancel, leaving 1 over root 15, which then rationalizes to root 15 over 15. All right, so we have our tangents. Now we can go ahead and plug into our formula. Tangent 2 theta is 2 times tangent theta, so 2 times root 15 over 15, over 1 minus tangent squared. Because I'm squaring, I'm actually going to work with the original unrationalized version, so my numbers don't get too large there. The numerator is going to give us a 2 root 15 divided by 15. Our denominator is 1 minus 1/15. So we have 2 root 15 over 15 divided by 14 over 15. Dividing a fraction means multiplying by the reciprocal. So the 15's cancel as the 2 and the 14 reduce. We're left with a positive root 15 over 7 for our tangent 2 theta value. All right, so that's all we're looking to do for our tangent 2 thetas here. Again, the process might be a little bit more complicated because we're trying to find tangent single theta. But it's still the same kind of fundamental identities from 7.1. Review that process if you have to, and then kind of just see how it works out when you're solving the problem. All right, so that's it for the double angle. So we doubled an angle. Next video is actually going to be talking about taking the half angle identity and seeing how that applies. So I'll see everyone next time for that.